Hi everyone. This is the second class in the number theory series. Uh, so, hi. I guess I can start now. Okay. Okay. So I'll just give you a brief of what all I plan to cover today. Uh, so I'll be starting with Fermat's little theorem, and then showing you Wilson's theorem, Euler's theorem, Chinese remainder theorem, and orders. And then you have some exercises which are for you to practice afterwards. I also added a list of resources I think you might like and find instructive. Alright, so I'll give you a brief introduction about the course and the lecture. This may be slightly repetitive for a lot of you, but some of you may also find it helpful. So this is the second lecture in the NT number theory module of the ZIS series run by CodeChef and an academy. The first two were on algorithms and searching, sliding, and sorting. Uh, I think you would like those lectures as well. You should definitely watch them. So ZIO is the first stage in the computing Olympiad program, and the format is there are 12 problems, 4 problems, and 3 subparts of each, and you have to submit an integer answer to them. The mostly test your algorithm thinking and informatics based intuition. Sometimes the problems are more direct, but usually you have to find an algorithm and then solve them. About me, I am a 12th grader from New Delhi. I'm from a mathematical background, a mathematical Olympiad background, rather than an informatics Olympiad background. I cleared INMO last year, and I'm also an IMO and an APMO medalist. I'm teaching the number theory module and the ad hoc advanced modules. I hope they'll be helpful to you and you'll enjoy them. So, is it good if I start now? Is it fine with everyone? You can just react if it's fine. All right, awesome. Okay, so I'll be assuming some prerequisites. The prerequisites are from the previous lecture itself. You should be familiar with the basics of modular arithmetic and you should know what the totient function is. The number of numbers less than a number which are co-prime to it. You should be fairly familiar with those if you've watched the previous lecture or even gone through the resources I've shared. Otherwise, you shouldn't have much trouble with the content we'll do. And if you have not seen these or are not familiar, I suggest that you go through them first and then watch the recorded version of the lecture, as you may otherwise have some trouble. All right. So I'll start with the main content. Yes, I'll okay. The totient function is just the number of numbers less than a number which are co-prime to it. So we actually worked on phi in the counting part of the basic counting results. If you may remember, we covered the number of factors and the sum of divisors as well. All right. Yeah. Can you just confirm if it is streaming on YouTube? Then I can start. Can anyone confirm if the YouTube stream is fine? Please confirm this once. Okay, awesome. So I'll start now. So the first thing we have is Fermat's little theorem. You may be familiar with this, or even if you aren't, I think you'll like the theorem. So as you can see, we have that P is a okay. Let's just change colors. Okay, yeah. So for any prime P and A, which is a number such that A comma P is equal to 1, we have A to the P minus 1. Okay, why is this not? I'm sorry. Okay, a to the P minus 1 is congruent to 1 mod P. Okay, this is weird. I'm very sorry. So this is basically what FLT states as mentioned here. The proof of this is actually very surprising. There are multiple proofs of this. You can prove it by the binomial theorem as well. You can prove it via neat counting on necklaces. I think That's available on the Wikipedia, but I'll go through the one which I find the simplest and the most instructive. So the basic idea is that you consider sets of 1 to p minus 1 and till p minus 1 to a. See that mod p, they represent the same sets because no two of these things are congruent mod p, as we have seen earlier as well when we were proving the Bézard's theorem. So, because all of these, none of these can even represent the class 0 mod p. So this set is same as this set. So we get that the product of all these numbers is same as the product of all these numbers mod p because they represent the same sets. So we get p minus 1 factorial is a into 2a into 3a till p minus 1a mod p, which means p minus 1 factorial is congruent to p minus 1 factorial into a to the p minus 1 mod p. And because p minus 1 factorial comma p is equal to 1, we can just remove it. So we get that 1 is congruent to a to the p minus 1 mod p. That's a neat proof, right? Did you understand? Uh, all right, DXP. Okay. So do you understand why these sets are same mod p? Yes, okay. So if they're same, you remember that we can multiply the elements. So we can get that p minus 1 factorial, which is 1 into 2 into 3 into till p minus 1, is congruent to a into 2a till 3a till p minus 1a mod p. So this is also p. You can take out the a's from each element, and you get that p minus 1 factorial is congruent to a to the p minus 1 into p minus 1 factorial mod p. So you get that a to the p minus 1 is congruent to 1 mod p. Do you understand? Okay, awesome. Can you give me a thumbs up if you understood? Awesome. Okay. Adarsh, your question is addressed. The slides are available on the Discord server, and Adarsh, your question is very generic, and I think it has been answered by others as well. I would not be able to discuss that here right now. Okay. I'll go through it once more. Sure. Uh, Again, I'll just I assume that you understand why these sets are the same, mod p. Now, because they're same, their product is also same, mod p. The product of all the elements must be same because they're the same set. The session should not take longer than 90 minutes. And p minus 1 factorial is congruent to, does you get, from each element a, 2a, 3a till p minus 1a. So there are p minus 1 powers of a, right? And the other elements are just 1 into 2 into p minus 1. That's p minus 1 factorial. Okay, I'm sorry, I don't understand why I'm having trouble with writing this much today. I'll try to improve that. Very sorry. So 1 is congruent to a to the p minus 1 mod p because p minus 1 factorial is co-prime to p because p is a prime and it does not divide any number less than it. Okay, so with that clear, I'll show you. I'll ask you a problem. Can someone answer this? I'll create a poll for this. All right. Try to figure out what these terms are, mod P and mod Q, and then hopefully find something nice. There are many of you here, but it would be great if you could try answering the problem. Okay. I see. Okay. So, okay, observe here that what is p to the q mod p? The answer is b, which is p plus q. Observe that p plus q, p to the q mod q is just p, and q to the p is just 0. So we get that this is p mod q. Similarly, this is q mod p. So, or if we consider the number p plus q mod pq, you'll see that it's p mod q and q mod p. So that satisfies the condition, and that thus the answer is b, p plus q. The answer is not 1. I think you may have mistaken because uh, in our statement for the Fermat's little theorem, it is p to the q minus 1 is congruent to 1 mod p, not p to the q. Alright. Is this cool for everyone? Can you give me a thumbs up if you understand? Alright, awesome. Okay. So you see that p to the q. Okay. Uh, how do I undo this? Observe that p to the q is congruent to p mod q because p to the q minus 1 is see that p to the q minus 1 equals 1 mod q. So p to the q is congruent to p mod q because I can just multiply both sides by p. So, and q to the p is obviously 0 mod q. So p to the q plus q to the p is congruent to p mod q. Q to same is congruent to q mod p. So mod pq, it's p plus q. Okay, great. I think everyone got it. Please try this problem. I'll create a poll. Yes, sorry. It would be great if you all could try the problem. Whether you get it or not is irrelevant, but at least try it. Okay, all right. So the answer is actually 62. You can see, like it's written here, that 256 to the 13 can be written as 256 into 256 to the 12. So 256 is 2 to the 8 to the 12. So this becomes 256 to the 2 to the 96. 2 to the 96 is congruent to 1 mod 97 because of Fermat's little theorem. So we get that this is equal to 256 mod 97. 256 is congruent to 62 mod 97 because 256 is 97 into 2 plus 62. So answer is D, 62. Awesome. Uh, Thumbs up. All right. Okay, great. Okay, now we have Wilson's theorem. Wilson's theorem states that p minus 1 factorial is congruent to minus 1 mod p, which is saying that p divides p minus 1 factorial plus 1. Did you understand the statement? So this is like 3 divides 2 factorial plus 1, 5 divides 4 factorial plus 1, and so on. Okay, this is just the statement of Fermat's little theorem. I'm just telling you what that means. Minus 1 you can bring to that side, so you get p minus 1 factorial plus 1 is congruent to 0 mod p, which means p divides p minus 1 factorial plus 1. Okay, so I'm just taking the examples now. So if p equal 3, then p divides 2 factorial plus 1. You can see this is true. Similarly, 5 divides 4 factorial plus 1, which is true because 5 divides 25, which is 24 plus 1. Similarly, we have 7 divides 6 factorial plus 1, because this is 720 and this is 1. So 721 is divisible by 7, right? Okay. So now how do we prove this? This is a very nice theorem. Okay, and does everyone understand the theorem statement at least? Okay, great. Okay. Induction. Okay, I don't see how you would approach it by induction. Actually, I have no idea how you would do that. Because it's very hard to induct on primes, at least this way. I don't really know what you're saying, but I'll tell you what I know about the proof. Do let me know after the session how you approach it by induction. Okay, so we only work for odd primes because for 2 it just means 1 plus 1 is divisible by 2. So remember for Bezout's theorem we had shown that for every a there exists x such that ax minus 1 is divisible by p, right? So if p divides ax minus 1, so p also divides xa minus 1. So if for a the number is x, then for x you can find the number a. So now you can divide the numbers into pairs where every number has is with its corresponding inverse. But you get one issue, which is what if some number has the inverse of itself? We try to find that case. So in that case, we would have that a square because a into a is congruent to 1 mod p, which means p divides a minus 1 into a plus 1. So a has to be now 1 or p minus 1. So we ignore those numbers for now. So the remaining numbers pair up into inverses. So we get p minus 3 by 2 pairs of all which are mod 1, 1 mod p. So the product of those is also 1 mod p. So we get that p minus 1 factorial upon p minus 1 into 1 is congruent to 1 mod p. So p minus 1 factorial is congruent to p minus 1 mod p. P minus 1 is just minus 1 mod p. So p minus 1 factorial is congruent to minus 1 mod p. Did you get that? Awesome. Can everyone just give a thumbs up if you understood it? Yeah, this is a very nice proof, a very nice idea, and just shows you how powerful inverses are. Okay, so now can you try this problem? Can everyone try it? Okay, I see. No, n does not divide n minus 1 factorial plus 1. That's actually false. The answer is 1 because we have p divides p minus 1 factorial for plus 1. This is only true for primes. For Wilson's theorem is only true for primes, not for general numbers. The, an- the answer is 1 because we have already seen that p minus 2 factorial, because here we saw p minus 1 factorial upon p minus 1, which is p minus 2 factorial, is congruent to 1 mod p. So here we have 31 minus 2 factorial is congruent to 1 mod p, where p is 31, right? Do you understand how we got that? Or give me a thumbs up if you understand the answer. We just use Wilson's theorem here. Wilson's theorem states, okay, see, what does Wilson's theorem tell us? Wilson's theorem told us p minus 1 factorial is congruent to minus 1 mod p. And while proving that, we had shown that p minus 1 factorial upon 1 into p minus 1 is congruent to 1 mod p, because we could have paired it into p minus 3 by 2 pairs. So here we were getting, if you actually divide it, p minus 2 factorial is congruent to 1 mod p. So we would have here, when you place p equal 31, because 31 is a prime, remember, 29 factorial is congruent to 1 mod 31. 29 factorial is congruent to 1 mod 31. So we get the answer as A. Okay, give me a thumbs up if you all got it. Okay, great. So moving on, try this problem. This might be slightly harder, but I think you should try it. Okay, so I'll give you a hint. You can actually write 1 as 41 minus 40. So you can actually make it 1 into minus 40 mod p, 3 into minus 38 mod p, 5 into minus 36 mod p, and so on. What will that give you? Okay, so only two people attempted this problem. Uh, they're all odds. Like 39 isn't prime, so I'm just skipping. And 1 isn't prime either. So yeah, they're just odd numbers. So you can write 1 as 31, 41 minus 40 equal minus 1 into minus 40. Similarly, 3 square is equal to 3 into minus 38. Okay, I see that some of you didn't even understand the problem. Mod 41, instead of that, let's try with 5. So for 5, we have 1 square into 3 square. We have to find this mod 5. That gives us 9 is congruent to minus 1. For 7, we'll have something different. We'll have 1 square into 3 square into 5 square. So this is 9, 25. So you have 225, which is congruent to 1 because 224 is equal to 32 into 7. So we have to find this for 41. So, okay, let's go back to the main thing. I'll just remove this. Okay, so similarly 5 square is congruent to 5 into minus 36, right? So we can keep listing it this way. So we'll get that the number is minus 1 to the 20th power. Observe that 20th power is because we have 20 of these numbers into 1 into 2 till 40. This from Wilson's theorem we know is minus 1. So we get that minus 1 to the 21 is our answer, which is minus 1. In the general case, this becomes minus 1 to the p minus 1 over 2 because there are p minus 1 over 2 odds. And here we get another minus 1, so this becomes minus 1 to the p plus 1 over 2, which is our general answer. This generalizes us, as you can clearly see here. Okay, did you understand? This is a slightly more complicated idea, but I hope you understand. Please, yeah, as Sunny says, please respond. Uh, if you did not understand it, could you tell me what's the issue or where you're struggling, so that I can make sure that you understand it well. Please ask questions if you have any, please. I see that you're still confused. Okay, see the modulus does not care if the number is okay. See, if the number is 5, I can say that it's congruent to minus 2 mod 7. Minus 2 is not equal to 5 in general, but this just means that 5 plus 2 is divisible by 7. P is any prime. P is any prime. For any prime, this is true. Similarly, when we say this is congruent to minus 1 mod p, that just means if I add 1 here, then this whole number will become divisible by 41. That's it's better if you're familiar and comfortable with modular notation. Okay. Others, is it fine? Is it fine for everyone? Please respond. Okay, great. So we can now extend Fermat's little theorem to all n, such that When are primes even other than 2? We are just working for odd primes. Yeah, it's fine. Uh, so we assume that a comma n equal 1, where so I mean we are taking two numbers a and n such that they are co-prime. So we can even say that a to the phi of n is congruent to 1 mod n. Okay, so this is actually you can say it's a generalization of the Fermat's little theorem, but it's pretty much the same thing because if n is p, then you have a to the p minus 1 is congruent to 1 mod p. But it's not hard to get that this generalization is actually not stronger than. The GCD is 1. We have covered this. This means a common. If I say this is the GCD and this is the LCM. Okay. So we can prove it with the exact same idea as we proved Fermat's little theorem. So if the numbers less than n, which are co-prime to n, are x1, x2, x5n, as they were earlier 1 to p minus 1, if the numbers are x1, x2, x5n, then mod n, x and ax are the same set, right? Because if I have ax1, ax2, ax5n, that's also all numbers are co-prime and none of them is the same. So all that gives us the same set. So we'll get x1, x2, x5n is congruent to a to the phi n, x1, x2, x5n. So 1 is congruent to a phi n. That means a to the phi of n minus 1 is divisible by n. For example, yeah, I mean that's just basic modular notation. We are assuming familiarity with that. Okay. So did you understand the proof? You just replicated the proof for Fermat's little theorem for here. You try to look at the set. Okay, for example, I'll take the number, uh, let's say 12. What's the set of numbers which are less than it and are co-prime to it? So 1, 5, 7, and 11. Observe that 5 of 12 equal 4. Now if I pick a number which is co-prime to it, let's say I pick 5. So we'll get 5, 25, 35, and 55. But now if you consider all these numbers mod 12, this is 5, mod 12, 25 is 1, so 1. 35 is 11, mod 12, because 24 plus 11. 55 is what? 7. So you in fact get the same set in some other order. See 1, 5, 7, 11. That's the same set. Similarly, if you do any number, you will always get the same set. So you have x1, x2, x5n, 1 into 5 into 7 into 11 is same as 5 into 25 into 35 into 55. Now I can take out 5 from each term. So that gives me 5 to the 4, which is phi of n. Yeah, this works for that, yes, of course. Phi of 4 is 2, and a is 3, so a 3 square is of course congruent to 1 mod 4. I mean, 8 is divisible by 4. So yeah. So 5 to the 4 into 1 into 5 into 7 into 11. And I can again remove these because all of them are co-prime to A. So I get that 1 is congruent to A to the 5 of n mod n. Did you understand? Phi of 4 is 2. That's what you have written. A to the phi of n. Mm. What's the issue? I don't understand the issue. You told me n is 4. Phi of 4 is 2. So A is 3. So 3 square is congruent to 1 mod 4. That's all you're saying, right? Yeah, so what's the issue? Okay, as Abhinav response, do others have any issues or doubts? If it's clear, you just give me a thumbs up. Okay, awesome. Uh, if this is fine, let's try this problem. I don't think why have you taken a to the n and I have not taken a to the n. Abhinav, you're mistaken. It says a to the phi of n. It's a to the phi of n, not a to the n. They're very different things. Here you have n, but this is phi of n. Phi of n is the totient function. I assume familiarity with that, otherwise you cannot progress. The number of numbers less than a number which are co-prime to it. You'll have to review the first session for that. It's there in the first session. I cannot go into that again, sorry. Okay, could you do this problem? Could you just try the problem, please? Okay, so here, what do we do? See, phi of 100 is 40, right? That's true, I think, because 100 is 5 square into 2 square, so the phi is 20 into 2, so that's 40. So by Euler's theorem, we get 3 to the 40 is congruent to 1 mod 100. So 3 to the 40, okay, I'm sorry, this should be 40, my bad. 3 to the 40, okay, oh, I'm sorry. This is 3 to the 45, that's my bad. It's congruent to 3 to the 40 into 3 to the 5. 3 to the 40 is just 1, so I can remove this. 3 to the 5 is 243, which is congruent to 43 mod 100. And observe that the last two digits just represent what the number is mod 100. So we get there the answer is 43. Is that fine? Okay, give me a thumbs up if it's fine. Alright. The next problem may look slightly scary, but don't worry, it's not that hard. Could you try this problem, please? Yeah, don't be scared. This is just to show you how powerful Euler's torsion function is. No, this type of problem won't be there inside I. This is just to show you how powerful, how to use Euler's torsion function, which may appear inside IO. So unless you are comfortable using Euler's torsion function on these type of structures, it becomes harder to use it on more complex or other structures because this tests your comfort with it. So now you are considering this number mod 51. Mod, so as we have learned by Euler's torsion function, we only care about the powers mod phi of 51, which is 32. So we have this is the power. And observe that this whole thing is divisible by 32 because 32 is 2 to the 5 and this whole thing is greater than 2 to the 5 and it's a power of 2. So I can just remove this whole from here. Now we care about this on mod 32. Again, phi of 32 we know is 16, which of course it divides all this. So we can remove all this and just make it 0. So we care about 2 to the 3 to the 0, which is 2 to the 1, which is just 2, not 51. Yes, that's it. It looks scary, but it's just the same idea. Uh, is that fine? Yeah, it looks insane, but it's actually just the same concept used on a different structure. If you have seen Euler's torsion function, this shouldn't be that hard if you're comfortable with it. Okay, let's move on. Now we have the Chinese remainder theorem. This is a very important theorem, and this is you should definitely be comfortable with this, and you should know how to find k. So here we have, if we are given a list of co-prime numbers, a1, a2, an, and we are given a list of another numbers b1, b2, bn, then we can find a number k which satisfies all these congruences. And it will be unique if it's in this set. That means that it's unique mod a1, a2, an. That's the Chinese remainder theorem. Does everyone understand the statement? Okay. Do you understand the statement? Okay, great. Others? Please be interactive, otherwise this becomes very hard for me to do. If I don't If I can judge how you are doing, uh, uh, for proving this, you don't need any prerequisites other than comfort with modular arithmetic, which is a prerequisite for this whole lecture today, which I've already told you. For proving this is not very hard. Okay, so for example, if I say I want to find a number which is congruent to 1 mod 5 and congruent to 2 mod 3. If I want to find a number less than 15, if I want these conditions, I can do it. I can find such a unique number, and for example, in this case, that number will be 11. So for any such congruences, B1, Bn, yes, these all are K. We are finding K, right? K satisfies all these congruences. So these are the congruences. If you can satisfy these congruences, you'll be fine. So that's what you're saying. We can find such a number that satisfies all these congruences. Is that okay? If you understand the statement, please give a thumbs up. Or if you're confused, please do a confused emoji. All right. Okay. What's the issue? I don't really. If you could explain me the issue, I'll go over it. But as such, I don't understand what's the issue. Okay, assuming that you understood it, I'll move forward. I don't really see what there is to explain in the statement other than I'm just saying that you can find a K which satisfies all these congruences. Okay. Now, because BI are just congruences, not I'll just restrict them to this set because other than that, that becomes irrelevant. So this there are A1, A2, AN mod, congruences mod A1, A2, AN because the set is just 0, 1, 2, A1, A2, AN minus 1. Those are A1, A2, AN values. So and every number will correspond to some set of values B1, B2, Bn mod A1, A2, An. And the set B1, B2, Bn can also just take A1, A2, An values because we can just B1 can take A1 values, B2 can take A2 values, Bn can take An values. So the number of values of this set is also A1, A2, An. So there must be a unique congruence mod A1, A2, An for every set B1, B2, Bn because you get a bijection between these two sets, between every congruence and these sets. Do you understand the proof of the Chinese remainder theorem? That such a value will exist. Okay, so if you have some set here, say this is a set, and here I have a set of equal size, and every number goes to some number here, and everyone goes to a different number, and every number must be coming from some number. So if there is A1, this set can take A1, A2, An values, and every set here takes a unique, every number here takes a unique set, and the number of values a1 is a1, a2, an, thus there must be a bijective function between these two things. So for every set b1, b2, bn, you can find a congruence. Is that fine? Is the proof that such a number exists is fine? Please react, otherwise I can't judge. Okay, not clearly. Okay, so for example, when we were considering mod 3 and mod 5, this can be 0, 1, or 2, right? And this can be 0, 1, 2, 3, 4, 5. So this, if I create a set x comma y, where this is x, this is y, this set can take 15 values, right? 3 into 5 values. This set takes 15 values. But if I take any number, say for example 12, I can correspond it to some set. 12 is, for example, 0 mod 3, so I can say it's corresponding to 0, and it's 2 mod 5, so it's congruent to 0 comma 2. I can create a set this way. See, for every number I create a set this way. Now, see, the number of these values and the number of such sets is equal, because both of them are a1, a2, an. Now, because these are the same things, must have that they are equal in size. I mean, they are equal in size. We have shown that, and we have injective function here. This is injective because everyone is going to a unique value. No two numbers, for example, 6 and 12, 6 will go to a different set as to 12. 6 goes to 0 comma 1. Every number must go to a different set, right? No two numbers can go to a, yeah. So because they're same and every number is going to a different set, every value must be coming from some number. Every set must be coming from some number. So we'll be able to find a value that corresponds to these congruences. Okay, if this is clear now, just give me a thumbs up. Okay, awesome. Now, in fact, we can actually find the value of this. How do we do that now? So if A is A1, A2, AN, remember we have shown that you can always find an inverse. So you can find a CI which is inverse of A2, of A upon AI, mod AI. Because this, if I remove, for example, A1, the remaining number is co-prime to A1. So I can find a inverse of it. Let that number be Ci for AI. Now, if I let the K equal A upon AI into Ci into Bi, what do we get? Think about it. So if I'll just check congruence with every number. For example, with A1, except the term where we are dividing by A1, every term is divisible by A1. So we'll have A upon A1 into Ci, which mod A1 just becomes 1 because we have defined Ci that way. This much becomes 1. So we'll have that this term is divisible, is congruent to Bi mod Ai. And the other terms are congruent to 0 mod Ai. So we get a K that satisfies our conditions. Is this cool? Is this fine? Is it fine for you? How we actually got the number that satisfies the condition? Awesome. So, okay. So now we'll move on to the next part. That is the review problem for the Chinese remainder theorem. Can you find the smallest such n now? I'll give you some time for it. Please don't try option by option, but actually find it using Chinese remainder theorem and then see which option your matches. Please don't just check option by option. That's not very helpful or instructive. As ZIO won't be a objective exam anyway. You have to actually find the value. Okay, great. Okay. Uh, it's fine. Okay. So we'll ignore the divisibility by 2 for now. The answer is actually 52. And we'll use CRT on the other numbers. So we can, because of the result we had shown, find what n is. Okay, so first we take 3 into 5 as we take 7 equal a1, so 3 into 5. Now we want to find the inverse of this mod 7, which is just 1. So I just put 1 here. 3 into 5 into 1, and we wanted the congruence mod 7 as 3. So we get 3 into 5 into 3 plus. Now if we want to, we'll check for 5. 3 into 7 is already congruent to 1 mod 5. So we don't need to add any inverse here to, to match, to make this 1. And we want the congruence to be 2, so we add a 2. Now 5 into 7 is congruent to 2 mod 3. And we want to find its inverse, which is 2. So we get the inverse as 2. Now we have now we get the number as 1, and that's what we wanted. So we get the value of this whole thing. Mod 105 is 45 plus 42 plus 70, which is 157, and which is 52 mod 105. So that the answer must be one of these values, and we want the value which is divisible by 2, which is 52. So that's our answer. Is that okay? Can others also reply? You can just give a thumbs up if it's okay. All right. Uh, okay. First we did 3 into 5. We found our inverse is 1. So we did 3 into 5 into 1. Now we want this to be congruent to 3 mod 7. Remember that what we were doing in Chinese remainder theorem was a upon ai, which is 3 into 5, into its inverse, which is 1, and then bi. So we have 3 into 5 into 3. Bi is 3, right? So 3 into 7, again into 1 because inverse is 1, into 2. 5 into 7 into 2 because the inverse is 2. Then and we wanted 1, so we just get 1. So 3 into 5 into 3 plus 3 into 7 into 3. Okay, awesome. Now let's try the new next problem. Try this, please. I'll create a poll. Okay. Okay. So try to break 230 into smaller factors. So 230 is, for example, 10 into 23. Uh, it's fine if you can't change the option, don't worry. If you find the answer, that's fine. The poll is just for practice. So mod, you can try to find it mod 10 and you can try to find it mod 23 and then use Chinese remainder theorem to get your actual answer. I added some time for you to try because I think implementing Chinese remainder theorem is a slightly longer process. I see that there is nothing special in it. Yeah, it's fine, Abhinav, don't worry. You're right. Okay. Alright. You actually got the answer. That's awesome. So first we'll try mod 10. Observe that mod 10 271 is 1 directly. So whatever the power becomes, it becomes very irrelevant. So we just leave it as 1 mod 10. And now we try mod 23. Mod 23, again we only care about the exponent. Mod 5 of 23, which is 22. 5. Observe that 67 mod 22 is just 1. So this becomes 271 to the 152, which is 271, which is 18 mod 23. So whatever our was, we had 271 is the answer was 1 mod 10 and we have also 18 mod 23, which you can already see directly. Here we had 271, here also we just had 271. So our answer must be 271 only. 271 mod 230 is 41. So that's our final answer. I think we should be done in about 20 minutes. We should be done in about another 20 minutes. Okay, if this is fine, I'll move on. Just give me a thumbs up if it's fine. Okay, awesome. So now we consider orders. Or this is a slightly harder and a more advanced concept. This may not necessarily be relevant for ZIO, but this is something which is quite helpful to know and is not that hard to understand either. So I'll explain it to you, but if you want, you can skip this part. The rest is just orders, and I'll be reviewing some things. For numbers a and n again, such that a and n are coprime, we call the minimum natural d such that a to the d is congruent to 1 mod n, the order of a mod n, and we denote it this way. And okay, if sorry to go back to this. If you want to skip this part in your recording, you can skip directly to the resources. I think you'll find those very helpful. and the practice problems as well. Sorry to put this in between. Back to the problem. Is the definition of an order clear? Could you give a thumbs up if the definition of an order is clear? Oh, okay. I see that most of you did not understand the definition itself. Uh, we call, so for example, when we would, let's take 5 and 12. 5 equal A and 12 equal N. So we want to find the minimum number such that 5 to the D is congruent to 1 mod N. Observe that uh, that number is not 1 because 5 is not congruent to 1 mod 12. Sorry. But 5 square is congruent to 1 mod 12. Whosoever is spamming, please stop. It's actually distracting and unhelpful. Uh, so number is 5 square is congruent to 1 mod 12. So we say that the order of 5 mod 12 is 2 because 2 is the smallest number such that this is true. Similarly, for any a and n which are co-prime, we define the smallest number which divides the uh, okay, sorry. This is enough spam. I'm blocking you, please. Please do not do this again. If you do this again, I'll have to block you. Please stop. So we define the order as the minimum number such that 5 to a to the d is congruent to 1 mod n. Okay. Uh, so someone is really spamming the questions and messages. It's actually quite annoying. Okay, so now we have the very important theorem that if k is such that a to the k is congruent to 1 mod n, then the order, which is d, will divide k. As you may see, this looks already looks very powerful, right? Okay, so now what can you tell? What's your intuition on how you can prove this? You can just type in the chat if you have any ideas how we could go about even proving this. Uh, any ideas? Yes, D is the order. Okay, so remember we learned something called the Euclidean division algorithm or the Euclidean division lemma. We'll use that to prove this. Now, by Euclidean division lemma, as k is greater than d because of definition of d, we have k equal dq plus r, where r is less than d. Now, from this, we have 1 is congruent to a to the k because we are given that, which is a to the dq plus r. So we can write it as a to the d to its power q into a to the r. As this is 1, so we have 1 is congruent to a to the r mod n, but r is less than d. So we have found a lower number, but by definition of d, this can't be possible. So r would have to be 0. So we'll have k equal dq. So we have d divides k. Nice, right? If you understand, let me know. If this is fine, you can give a thumbs up. Yeah, as I mentioned, orders is not very relevant for ZIO, but it's a powerful idea, and the idea of how you prove orders work, the idea of infinite descent is very helpful in general as well. As I mentioned, you can skip this part if you want to. Orders is not very relevant. Okay, got it. Nice. So yeah, this is a very nice theorem, and this will give you something very important, that the order. Yeah, we'll be going through practice problem. Don't worry. So D, which is the number here, order, will always divide phi of n, because we have a to the phi of n is congruent to 1. So we have d divides phi of n, which is obviously very nice. In case, for example, let's say n is p, then we have d divides p minus 1. Or if we have, let's say p minus p is like, if you can somehow get p minus 1 is a very nice number. For example, say it's 2 to the k, p equal 2 to the k plus 1. This is just an example, this is not a particular case. Then you will have that d divides 2 to the k. So d is the power of 2 itself. So you can get very nice things this way. Orders are actually very powerful. So for that, please try this problem. Practice problems are for you to try. I'll be showing them, and they're in the PDF itself, and I've shared the PDF with all of you. Uh, okay, so try this problem, and I'll show you a couple other examples of orders as well. Okay, let me try to create the poll again. Yeah. Oh, what happened? Okay, okay, I see. So observe the very important thing. If let's say the order of A mod 17 is D. Sorry. Let's say the order is set D. Then D divides 16, as we have shown, because mod 17 and A to the P minus 1. So D divides 16. And also, because of our definition, A to the 146 is congruent to 1. So D divides. Okay, I'm sorry. My mouse just stopped working. Yeah, okay, sorry. D divides 146. If these two things are true, then D must divide 2. If D divides 2, it's either 1 or 2. So 17 will divide A square minus 1. So A must be plus or minus 1 mod 17, because 17 divides A minus 1 into A plus 1. So it must be either plus or minus 1 mod 17. And the only option which does not satisfy plus or minus 1 mod 17 is 117. So A is not equal to 117. Is that fine? Yeah, okay. I'll go through it again. See, here we showed that D divides phi of n, right? When n is a prime, so we get that D divides P minus 1. Here, P is 17, so we get that D divides 16. And because of our theorem that if a to the k is congruent to 1 mod n, then the order must divide the power. So sorry, this is here and this is nothing. Order 17a divides 146. Now 146 is 2 into 73. But our order must divide 16 and 2 into 73. So it must divide 2. Because 73 is kind of irrelevant. It can't be here. So D divides 2. Yeah, the recording will be available on Unacademy and YouTube. So order of A, 17A divides 2. So the number must divide either A minus 1 or A square minus 1. In case it divides A square minus 1, you can factorize this. Okay, yeah, you can check it later. Enjoy. A minus 1 into A plus 1. Bye. So 17, if it divides this number, it might divide one of these. So it will be either 1 mod 17 or minus 1 mod 17. But only the only number which does not satisfy this is 117. So A cannot equal 117. You can see that 86 is 1 mod 17, 33 is minus 1 mod 17, 1784 is minus 1 mod 17. Okay, awesome. So I'll be with this. I understand that I hope you got it. I hope you enjoyed it. But I understand that the lecture was quite theory heavy, and a lot of it may not be completely clear, or because I did not may have not been able to satisfy it completely or do it justice because of the speed I was going at. But if you should thus look at it again or go through it through one of the resources I've shared. I have also added some harder problems for you to try and some very nice resources that I like. They're all freely available, so there are no copyright issues or anything, and you can just try them as you want. If you still have trouble with the problems, CRT can come up in ZIO. It can come up. I don't remember exactly, but I think I've seen it. Yeah. If you have, you can ask me after the session. You can just contact me on the Discord server. Uh, and if you want to keep in contact after the series ends as well, just let me know. I hope you enjoyed the lecture and please fill the feedback form. Okay. And as there are, I have added a couple of problems here. These are computational. This is an application of orders, so you should try it. It's an AIME problem. So orders. This is also application of orders. So you will actually learn quite a bit if you try these and you'll get slightly comfortable with orders. This is slightly easier problem that you should try. Then these are quite proof based and these problems you can leave it if you want to, but these are good practice and good ideas. You should at least know this one. And after you've done the modular arithmetic basics, you'll be comfortable with this. This won't cause you any problem. These are two additional results which I did not include in the set due in the lecture due to time constraints, but these are things you can know. This is called Fermat's Christmas theorem, and this is just primitive roots. Please stop. I'll seriously ban you from all the lectures. Just don't. Uh, okay, thank you for removing that. There are few other resources. The presentations are of course probably helpful to you, and I really suggest that you look through it again. Or even if you don't look through the lecture, you should look through the presentation. That's available on the Discord server and I think on Academy as well. Then I like Aditya Khurmi's new book, which was released just a few days ago or a week ago or so. This is a very nice book and very comprehensive. The first two chapters are more on modular arithmetic and maybe more relevant to you, you should also look through the basics of the chapter constructions. That's chapter 9. This is a very nice book. You should definitely go through it. I like Stanford's notes collections on number theory. I've done a fair number of topics from there. Brilliant.org is, of course, brilliant. Uh, there's They have a lot of number theory resources, both a lot of which I've shared with you already, and I suggest that you go through as many as you can. Michael Penn's number theory playlist is highly recommended even by the students in the. Yeah, all of these are freely available. None of them are paid. Highly recommended even by students uh, in this program. A lot of you have even sent me suggestions about this. So yeah, I think you can try this. This may be quite instructive for you due to the speed I've gone at. Other than that, number theories from the IMO shortlists are of course nice, but they can be extremely hard at times. So if you want some easier and more computational type problems, PUMAC, the Princeton Mathematics Competition, is quite impressive in that. I borrowed a lot of my problems for the problem sets from there. For more informatics and coding related practice, you can always try Project Euler. That's a brilliant resource. And that's thanks for attending. You can again my Discord username and you can just tag me on the survey if you have any doubts. If you don't feel like DMing me, also please fill the feedback form. I'm sorry for the theory heaviness, and I hope you enjoyed. Uh, okay, that's possible, but I don't think it's happening because on my screen it seems fine. Please fill the feedback form, and I hope you enjoyed it. Thank you. Bye, everyone. Can you just tell if it's fine or if you have any issues? I can address them right now. We still have about 5-6 minutes to go. Okay, I'll look through the YouTube chat once if there is anything important. Don't address me as well, please. Just call me Rohan. Okay, there doesn't seem to be anything on the YouTube chat. Alright. Thank you, everyone. Thanks for attending. I hope you enjoyed. Bye.